For this presentation, we will be using a real-world example of a multi-stage gas compressor used to transport natural gas by pipeline from areas of production to areas of consumption. As illustrated here, compressor stations are generally located every 50 miles or so along the pipeline to increase pressure, and thereby move the gas along the route. Let's take a look at one compressor station along this pipeline. This compressor station uses reciprocating piston compressors that allow the gas volume to be adjusted to meet the demand. These are the sensors on the equipment that are available to provide data for machine learning. In this example, all 4 compressors are identical, which will allow what we learn about one machine to be shared with the others. Since this compressor went into operation, a series of critical failures has caused expensive repairs and serious interruptions, resulting in reductions in available gas moved to consumers, as well as financial losses to the producers of the gas. Mtell Previse extracts and uses data from 2 primary sources, the asset management system and the plant historian. Data from both sources are combined to implement machine learning. First, Mtell downloads the equipment hierarchy and descriptions from the asset management system. Each asset has an identification tag, or asset ID. Then, using data imported from the plant historian, Mtell associates the name tags of the sensors with the correct assets. An equipment set comprises similar equipment with the same sensor configuration that can share learned behavior between one another. In this example, 4 compressors make up the equipment set. Here, each compressor has the same sensors with slight differences in names. A sensor template is the master structure holding the asset information and sensor tag metadata for a piece of equipment. A sensor role is the generic name and function for a specific tag. Once configured, Mtell Previse imports historical data from the plant historian and work history from the asset management system for each member of the equipment set. A training dataset contains all the sensor data for one asset for a specific period of time that contains both normal activity and behavior when degradation and failure occurs. Applying the work order events from the asset management system over the historical trends indicates where the failures occur. This stimulates the process to learn the precise signature that led up to the failure. This automated process learns known failure signatures that are indicated by work orders from the asset management system, in addition to signatures that show deviations from normal operations, also known as anomalies. Both failure and baseline signatures are used to create machine learning agents. Machine learning agents continuously monitor live data streams coming from the plant historian system to detect patterns that show recurrences of known failures and anomalies. On detection of anomalies and failure patterns, the agent issues email, SMS, and dashboard alerts, in addition to generating and placing work orders directly into the asset management system. When anomalies and failure patterns occur, a sensor tag ranking chart offers predictive root cause guidance. For known failures, notification is very specific with an accurate time to failure. Notification also includes an announcement of the precise failure code from the asset management system, indicating the type of degradation and the action necessary to avoid or mitigate the failure. Once patterns are learned and deployed on one compressor, they are rapidly transferred to the other compressors. After a very short retraining period, every compressor now has the same safety and breakdown protection.